So it's a question of LC-WC-374 contest. Count complete substrings. So in this we have given a string word and an integer k, and there are two conditions for a substring, that each character in S occurs exactly k times, and the difference between two adjacent character is at most 2. These difference is will be taken by the positions of the character in the alphabetically. For example, if we have the A and B, so the difference between the A and B is 1, and A and C is also is 2. So in this, at most 2 is only available, or we can say that we can take it. If we talk about A to D, then the difference will be 3, and it will not be valid, as the value of the K will be 2. Difference is 3, but the positions will be at a difference of 3. So here we can take an example. A word IGI, and K is equals to 2. So we have 3 strings here, which are satisfying the conditions. IG. So we have the GHI, and the difference between the G and I is 2. So it is valid. And in the next EE, so the difference will be 0, which is also valid, as we can have the at most 2. And for the whole string IGEE, that is also valid. And there are the constraints that the word dot length means that the length of the word can be from 1 to 10 to the power 5, and there is a constraint that word will only contain the lowercase letters, and K will be between the 1 and word dot length.
So in this question, the prerequisites are we need to have some basic understanding of sliding window. And also so basic understanding of sliding window and understanding how time complexities work. So let's see. Let's take this example test case to dry run our question. All right. So what we basically do is, from this information, we have been given that the k value is 3, right? And which means that every character in the substring should have at least 3 occurrences, right? Now, what is the total number of unique characters in alphabet? We have total 26 unique alphabets, right? So what is the maximum length of substring that can be formed? It will be 26 into k, right? Like if there is a substring beyond this length, then it will have some character with an extra occurrence, right? So that substring will not be considered, right? So what we can say here is that the maximum length of a substring will not exceed 26 into k, and every substring will be the length of every substring will be a factor of, a multiple of k. So the substring might be k, or length 2k, or length 3k, or length 4k, so on till length 26k, right? So these are fixed lengths will always be the answer. So like because every character will need to have k occurrences, right? Now what we can do is, for every one of these lengths, so from k till 26k, for every one of these lengths, we can fix one sliding window, and for that sliding window, we can brute force the solution over all such possible substrings. So let's take this word in our test case. So we have AAA, BBB, CCC, right? So let's take first for a length of k, which is 3. So for 3 length, we will have this substring first.
Yes.
So we take the first sliding window. Now we also need some basic understanding of how a hash map works. So map just to show the frequencies of characters, because in sliding window we cannot possibly go through every substring every single time, because sliding window is used for optimization.
Yeah.
So what we do here is, first we take these first 3 characters. So we have a map. Let's just say this is the map. All right. In this map, A has a frequency of 3. Now that we have this information, we move the sliding window a little bit ahead. So now this is the sliding window. Okay. Now when we move the sliding window, we basically subtract the frequency of the character which is removed and add the frequency of the character that is added in the sliding window. Okay.
Okay.
So now the new frequency will be A equals to 2 and B equals to 1, right?
Yeah.
So in such a way, we move the sliding window and keep track of the frequency, right? So let's just go back to the initial sliding window. So now in this sliding window, our frequency of A is 3. And once we have this, we iterate through the entire map. We go through the entire map and we see the characters of the frequencies of each letter, each character. So now here the character of A is 3 and there is no other character.
Yeah.
And our condition is that every character must have a frequency of 3, which is the K value. So if there is some character which has a frequency that is not equal to K, then we can just say that that substring is not possible. Like we cannot take that substring into our answer. So for this first substring, the answer will be incremented. Basically, we can add to our answer one possible substring, like this is possible. So now in the next, when we move the window, now we have 2 A's and 1 B. So basically A will be 2, B will be 1. Now it's not possible because K value 3 is not satisfied here and here both.
Yeah.
So if you observe in such a way, if we keep moving the sliding window for the K value as size 3, I mean for the window size as K, we get this one possible substring, this one possible, and this one possible. So we have 3 total possible substrings. So for K window size 3, we have 3 possible substrings, right? Okay. Now let's move to the next possible substring. So we have 2K size, right? So now let's take 2K into consideration. So size is 6, 2K is 6. So in the first substring, our map will be A equals to 3, B equals to 3. So frequency of each character is 3. So our condition is satisfied. So we got one more substring. And if you observe, the next possible substring with size 6 will be this one. So these three, where the frequency of B will be 3 and frequency of C will be 3. So for the size 2K, we got two substrings. So let's just say plus 2, right? And now let's check for size 3K, which is basically 9. So for 9, there will be only one substring, which is the entire string. And for this, the frequency will be A equals to 3, B equals to 3, and C equals to 3, right? Okay. So there is one more substring. So the total number of substrings will be 6 in our case. And if you go through we check the sample case, the answer is 6 here. All right. But now there is one more thing that we need to keep track of, because they have mentioned in the question that every adjacent character should have the difference of at most 2. Now in this case, we were lucky because everywhere, like between AB, between BB, between every other character, the difference is less than 2 only, right? Equal to 2 or less than 2 in all the cases. So we were lucky in this case. But what if there was a different situation? In that case, our answer might not have satisfied. So what we do to handle this is, let's take like a little example. So let's say we have I, A, and then let's say A. All right. Let's say this is the string. This is the word. This is the word, and K value is, let's say, 2. Okay. Okay. Now in this, if we use the previous approach, we will get this as a possible answer because A has 2 frequency, I has 2 frequency. Yeah. But the difference between I and A is a lot more than 2. So, so it doesn't satisfy condition, but it's still being included in our answer.
Yeah.
So let's see how we can fix this. I'll add another variable. I'll call it mark, or let's call it difference. So let's call it diff index. Okay. Initially, I'll say that this variable is -1. Okay. Now, when I'm every time I make a new sliding window, let's say now since k is 2, at some point we will get 2k as window size, which is equals to 4, right? 2k is 4, right? At some point I'll come across this point, and in that case I will have to take the first substring, right? Now here diff index is initially -1, but when I take the first substring, I have to iterate through each one of these and check whether there is a point where two adjacent characters are different. Okay. So here we get that between I and A, the difference is more than 2. So we'll say this diff index is 0. Okay. 0 indicates the position where it is different. So which means, like, until now, while iterating, we have gotten till this point. We know that these both are different. Let's see what is ahead.
Yeah.
Okay. So here, when you come at this point, again A and I difference is 1. So we'll make this as 1, and you move ahead here. Then you make this as 2 because it's still different, and you'll move until this point where it's the same. So basically, diff index will point to 2, which means until the point 2, before elements before the point 2 have some difference in their adjacent elements.
Yeah. So
that cannot be considered. So next time, if I'm taking a substring from of size 4, okay, I'll just erase this part and write it here. Let's yeah, okay. But if let's say I'm considering this index, this substring,
okay,
and I know that the diff index points to 2, okay,
yeah,
and I know the end of this one is which is 2, 3, 4, 5, which is 5. Okay. Now, if I do 5 minus window size is 4 equals to 1. Now, this 1 value goes before the point where our diff index point is, which means we don't have to check the frequency condition. We know that the answer clearly does not exist. Okay. Because at some point previously, there is one point where the adjacent elements are different, right?
Which are not satisfying the conditions.
Exactly.
Okay.
So, and if we move ahead, we come to 6. So we say 6 minus 4 equals to 2. This is equal to diff index. Now we are using a convention where if it's equal to diff index, it's fine. But if it goes before that, then it's not fine. So equal to diff index. Hold on a second. No, diff index is 2, right? So yeah, okay. Equal to, if it's okay, this is not 6, right? 2, 3, 4, 5, 6. Okay. Yeah. So if it's equal to diff index, then that's fine. But if it's going before that, below that, then it's not fine. Right. So what we do is, first condition we check whatever the end of the sliding window point is. We subtract that from the window size, and we check if that value is more than or less than equal to diff index. Okay. And what we do is we increment this diff index every single time. So in the previous test case, I said that we have to increment the map. So every time we slide the window, we add the frequency of the next character and subtract the frequency of the previous character. Right. Yes. So every time we do that operation, we check this condition. We check the next character and the previous character condition. If it's different, we update this value. Okay. Okay. So in this way, we can solve this question. Now let's see the time complexity of this question. So we go from K all the way up till 26K, right? and for every one of them, we run a sliding window.
Yeah.
So we can say that the complexity is 26n. Hold on. Okay, not these are 26 different sizes, right?
Yeah.
And so it will be 26n. Like for every sliding window, our complexity is usually off and only because sliding window can happen once. In one
Yes,
shot, we
yes.
can go. So for 26 different window sizes, we can do it in 26n.
Yes.
Right. But for every sliding window, we also need to check this map condition, right?
Yeah.
So in map, we have to traverse and check if every element has the frequency of k, frequency equal to k or not, right? So there will be an added 26 complexity. So it will be 26 square into n, right? Okay. So yeah, this is how we can solve this question.